Early telecommunications relied on circuit switching. To send information, the system had to establish a dedicated, continuous physical path between the sender and the receiver before a single piece of data could travel. This rigid structure created two massive bottlenecks. Setting up that dedicated connection caused significant delays, and if the transmission paused, the physical channel sat idle, wasting bandwidth that remained unavailable to other users. Packet switching provided a more flexible alternative. Instead of monopolizing a single line, data is shattered into small, independent blocks, packets, before entering the network. Because these packets travel independently, multiple users can share the same network resources simultaneously. Bandwidth utilization reaches maximum efficiency, and the network gains automatic fault tolerance, allowing packets to dynamically route around and bypass failures. But shattering data into millions of independent pieces introduces pure chaos. To reassemble those packets accurately at their destination, engineers needed a standardized set of rules. This alignment chart compares the two resulting frameworks. The theoretical OSI model strictly separates network architecture into 7 distinct layers, but the TCP/IP model, developed by DARPA, proved more efficient in the real world by collapsing the session, presentation, and application layers into one. That 4-layer TCP/IP architecture, driving a packet-switched network, provides the exact logic necessary to guarantee data delivery over a shared, unpredictable global infrastructure. By design, the packet-switched network is connectionless, with no built-in mechanism to prevent data loss. Therefore, reliability must be enforced at the transport layer. This is the domain of TCP, the Transmission Control Protocol. TCP acts as a connection-oriented engine, taking responsibility for the accurate, sequentially ordered delivery of every byte. TCP forces a strict 3-way handshake. First, the client initiates contact by sending a SYN request. The server responds with a SYN ACK. Finally, the client sends a concluding acknowledgement, locking both into a connection-established state. TCP encapsulates application data alongside specific control fields. The sequence number identifies byte order, while the acknowledgement number confirms receipt. Meanwhile, the window size field executes flow control, preventing a fast server from overwhelming a slower receiver. TCP stabilizes a chaotic environment by forcing strict mathematical accountability onto every transmitted byte. Once the TCP segment is built, it drops down a layer in the stack and is encapsulated within a connectionless IPv4 datagram. IPv4 physically routes these datagrams across different network segments, relying on the logical source and destination IP addresses embedded in the header. But routing across millions of interconnected devices creates the risk of routing loops. A misdirected packet could bounce endlessly between nodes, eventually consuming all bandwidth. In the IPv4 header, the time-to-live field acts as a strict packet lifetime counter. The integer degrades by 1 at every router hop. If it hits 0, the router destroys the packet. IPv4 relies on TCP to catch and resend lost data, but this built-in self-destruct mechanism ensures that isolated routing errors do not cascade into total system failure. To process these datagrams efficiently, routers utilize subnetting. They divide large IP spaces into smaller, isolated subnetworks to reduce congestion and speed up delivery. When a router receives a packet, it executes a high-speed calculation using the starting IP address and a CIDR mask to find exact network boundaries. Consider IP 10.20.30.45/28. The router expands this to mask 255.255.255.240. Subtracting the mask from 256 yields block size 16. The closest multiple before 45 sets the network address at 10.20.30.32. Adding 15 establishes the broadcast address at 10.20.30.47, leaving 14 usable hosts. Subnetting acts as a brutal, instantaneous binary filter. It allows edge routers to make directional routing decisions based entirely on logical arithmetic. But abstract routing math eventually meets physical reality. The datagram must transition onto a local area network, moving through actual, unforgiving electrical cables. A common early physical arrangement was the bus topology, where all devices on the network physically tapped into a single central backbone cable for bidirectional transmission. This exposes the core vulnerability of any shared physical medium. If two nodes transmit at the exact same moment, the pulses collide on the wire, corrupting the data. Early networks used a random access protocol called Pure Aloha, which permitted nodes to transmit payloads whenever they wanted. The collision rates were devastating, capping maximum network efficiency at a dismal 18%. This chart illustrates the first fix. By shifting to slotted Aloha, engineers reached 36% efficiency simply by dividing time into discrete slots and forcing nodes to delay transmission. Today, networks use a sophisticated control mechanism called Carrier Sense Multiple Access, or CSMA, to govern the shared medium. Instead of blindly transmitting, nodes listen to the wire first. Modes like non-persistent and p-persistent CSMA force devices to wait randomly or transmit with a specific probability when the channel is busy. Managing a local network requires orchestrating the microscopic silences between nodes. Pushing data forward only works when protocols prevent signals from physically colliding and destroying the payload. Zooming out from a single LAN, we reach the Wide Area Network, or WAN. WANs integrate thousands of local networks across cities and continents, creating the global map we recognize as the Internet. Because WANs utilize public shared communication links, they operate in an untrusted environment where security risks multiply. To counter this, modern networks implement Transport Layer Security, or TLS. This cryptographic protocol supersedes the older SSL standard. Operating just above the transport layer, TLS protects the payload's integrity by applying strong encryption algorithms and rigorous authentication mechanisms before TCP even begins its handshake. The complete stack functions as a unified mechanism. TCP establishes accountability. IPv4 and precise subnet math execute the global routing, and CSMA prevents physical degradation on the copper and fiber wires. Layered protocols maintain accuracy at scale by engineering mathematical order directly into the transmission process. This logic transforms inherent network chaos into a reliable global system.